Today we'll be covering multi-agent AI orchestration. So when you're designing AI applications, choosing between single agent and multi-agent architectures is very important for your business, especially affects everything from latency, cost, and your system's overall maintainability. Let's talk about when you actually need multiple AI agents instead of just one. The single agent approach starts to fail in three key scenarios. First, complex workflows that need specialization. Imagine building a system that analyzes legal documents, extracts financial data, and generates executive summaries. A single agent trying to handle all of this will struggle because each task needs different expertise. The prompts becomes bloated and the quality suffers across three different tasks. The second scenario will be when you need parallel processing for speed. If you're, let's say, researching information from five different data sources sequentially with one agent, your latency is just going to add up. Running specialized agents concurrently can dramatically cut your total time. Third is separation of concerns for maintainability. When a single agent handles too many responsibilities, debugging becomes pretty painful. So, what part of the prompt could be causing a failure will be really hard to debug. So, now let's talk about what are the advantages do multi-agent systems gives you. Specialization means each agent focuses on one domain with a tightly scoped prompt, which typically improves quality. Concurrent execution reduces latency because you're only waiting for the slowest agent, not the sum of all of them. Independent scaling lets you scale bottleneck agents without touching the others. And fault isolation improves reliability because if one agent fails, others can still continue. However, there are still trade offs. The number one is that the orchestration complexity increases significantly. You need coordination logic, error handling across multiple components, and monitoring for each agent. Token costs go up because you're making multiple LLM calls. Coordinated overhead also adds latency. State management becomes pretty critical because agents then need to share context as well. Also, the debuggability across agent chains become much more hard. The decision to use multiple agents should be intentional and not by default. You're trading simplicity for capability, and the trade-offs need to be worth it for a specific use case. Understanding these trade-offs upfront helps you avoid costly architectural mistakes that could be really important for your business later on. Now let's talk about the sequential pattern, which is the simplest way to orchestrate multiple AI agents. Sequential orchestration works like a pipeline. Agent A completes its task first, and then its output becomes the input for, let's say, Agent B. Agent B processes the information and passes the results to the next agent. Finally, the last agent produces the final outcome. This pattern shines in three key scenarios. For example, the first one is document processing pipelines are natural fit for this. You might have one agent extracting raw text, another one cleaning it and structuring it, and a third agent summarizing it. Multi-step analysis workflows also benefit from it. For example, an agent it retrieves the information, and another agent analyzes it for insights, and then a third agent could be formatting those insights. Quality refinement stage work well here as well. A drafting agent followed by an editing agent followed by, let's say, a fact-checking agent. So these are the main scenarios for sequential agent orchestration. Now here are the production considerations that you should consider. Commutative latency adds up pretty fast. If each agent takes, let's say, 3 seconds, a 5 agent chain will take around 15 seconds. This can violate your latency requirements pretty quickly. So here's a critical risk specific to the AI, which is the hallucination cascading. If agent A hallucinates some information and presents it confidently, agent B will also accept that hallucination as a fact and build on top of it. Then agent C will amplify that error further. By the end of the chain, you might have a complete fabrication and hallucination that will sound very confident and sound truthful, but they won't be actually true. So this is what hallucination cascading looks like. So related to this is the silent failures, which also compound downstream. Unlike traditional software system where errors throw exceptions, LLM agents can produce plausible sounding but incorrect outputs. Each agent adds another layer where this can happen without any hard failure signal. You will need retry logic per agent because failures can occur at any stage, and cost equals the sum of all agents, which gets pretty expensive in production with thousands of requests. Sequential patterns are powerful for multi-step workflows, but they do require careful attention to error propagation and latency management. When you choose this pattern, make sure you have monitoring in place to catch the cascading errors pretty early in the process. Now let's talk about the parallel orchestration pattern, which solves the latency problem of sequential chains. In parallel orchestration, multiple agents process information at the same time. Each agent handles a different aspect of the task independently. An aggregator then combines all the results into a single coherent output. The key benefit here is that the parallel execution reduces total latency pretty significantly. So, where does this pattern excel? Research across multiple sources is ideal for this. If you need to gather information from academic papers, news articles, and internal documents, and then you can have three agents working parallelly at the same time, and then each will be specializing in one source type. Independent task decomposition also works pretty well here for this use case. For example, let's say you're analyzing a product. One agent evaluates the technical feasibility, another assesses the market demand, and a third agent could be analyzing competitive positioning. These evaluations are pretty independent, so they can run parallelly. Time sensitive operations especially benefit when latency is your primary constraint. But here are the production realities. The pattern is bounded by your slowest agent. If your four agents finish in 2 seconds but the one takes 8 seconds, then your total latency is 8 seconds plus aggregation time. This is a staggered problem and it defines your speed. If you must handle partial failures gracefully here as well. So what happens if two agents succeeds but one fails? Do you wait for the timeout or do you proceed with incomplete data? These decisions need to be explicit in your design. Result aggregation logic becomes pretty critical and complex. How do you combine potentially conflicting information from different agents? Voting, weighted averaging, or let's say having an additional agent to resolve the conflicts. This aggregation needs careful design here as well. And peak token usage spikes can also hit your rate limits. When all agents fire simultaneously and in parallel, you're consuming tokens at a maximum rate. With multiple concurrent requests, you might hit API rate limits you wouldn't encounter with sequential processing. Parallel patterns gives you speed, but they do require sophistication coordination logic to handle the inherent complexity of concurrent operations. When latency matters more than operational simplicity. Let's talk about the hierarchical pattern, which is also called the manager worker model, which adds intelligent coordination on top of the parallel execution. So here how it works. A supervisor agent plans the overall workflow by looking at the task and decides how to decompose it. The supervisor delegates the subtasks to specialist worker agents. Workers then execute the tasks in parallel. Finally, a supervisor synthesizes all the worker outputs into a final result. This pattern excels at three key scenarios. Complex decision making is where the task itself requires, let's say, the strategic decision making before about the approach is number one use case for this. Dynamic task decomposition, where the supervisor looks at a specific input and decides which workers to involve in and how to order them, is pretty ideal for this. Adaptive workflow routing is also important, where the supervisor adjusts based on the intermediate results. Now, for the production considerations, the supervisor is a single bottleneck. Every request goes through this coordinator, so it needs to be fast and reliable. If the supervisor is slow or unavailable, your entire system will stop. Here is a critical issue specific to LLM based supervisors. Context window saturation is where it actually becomes pretty critical. If you have 5 workers that each return 1000 tokens of detailed results, that's 5000 tokens the supervisor needs to process. Add the original task context and the supervisor reasoning, and you quickly hit context limits. When this happens, information gets truncated or lost and degrading the final output quality. Planning adds initial latency before any real work begins. The supervisor needs time to analyze the task and create the execution plan. This upfront costs work for complex tasks, but this might not make the sense for simple ones. The worker coordination overhead is another factor here. The supervisor manages workers, collects outputs, and handles failures and orchestration retries as well. This coordination logic adds system complexity here. Finally, you need recursive depth limits. Supervisors can theoretically delegate to other supervisors, creating nested hierarchies. In production, you need explicit limits on nesting depth, or you risk unbound execution times and costs. The hierarchical pattern is powerful for complex tasks, but it does require careful management of the supervisor's context and coordination overhead. Use it when the intelligence of dynamic workflow planning outweighs the coordination costs. Let's talk about how AI agents actually communicate and coordinate with each other, because this is where the production systems actually get pretty complicated. For message passing, you have several architectural options. Direct agent to agent messaging is simplest, but it doesn't scale well. A central message queue gives better decoupling and allow persistence and event-driven pub/sub models work well when you have multiple agents reacting to the same events. Shared memory coordination can work for tightly coupled agents in the same process, though it does limit scaling options. State synchronization becomes pretty critical in multi-agent systems. You need some form of distributed state management, and the question is here how strict your consistency requirements are going to be. Here's what's crucial for AI agents specifically, which is the structural output enforcement. When agents communicate in natural language, is going to be pretty chaotic. Agent A might output something slightly different from what Agent B expects, and then you get parsing failures or misinterpretations. Instead, you can enforce JSON schemas for agent to agent communication. This makes output predictable and machine parsable. The JSON schema validation should be mandatory at every agent boundary. If an agent produces output that doesn't match the expected schema, you cache it immediately rather than letting malformed data propagate. Eventual consistency is acceptable for many workflows. Unlike financial transactions, if agents work with slightly stale data for a few hundred milliseconds, it often doesn't matter. This gives you architectural flexibility. Log-free designs reduce contention with high concurrency here as well. Structure your agents so that you don't need to acquire logs on shared resources when possible. For coordination patterns, standardized system prompts are pretty foundational. Every agent should use consistent terminology and output formats. Request response works well for queries needing synchronous answers. Fire and forget is appropriate for notifications. The Saga pattern handles distributed transactions across multiple agents, and circuit breakers per agent prevents cascading failures. Now, communication architecture might seem secondary, but in production multi agent systems, it's often where reliability issues actually emerge. Getting this right from the start prevents painful debugging sessions later when you're actually trying to figure out why agents aren't coordinating properly. Now, let's talk about state management in multi agent AI systems, which is one of the most important design decisions you should be spending time because it affects both capability and operational complexity. Stateless agents have no memory between calls. Every time you invoke the agent, you pass in all the context it needs. The agent processes, produces output, and forgets everything. This gives you simpler scaling because you can route any request to any instance. Reliability improves here because there is no state to corrupt or lose. Operational complexity is also lower because you don't need to manage persistent storage. Stateful agents maintain conversation memory across interactions. They use session based context retention, remembering what happened earlier. This enables complex multi turn workflows where each interaction builds on previous ones. But stateful agents they do need a persistent layer, typically a database or a cache, so survives so that even if agent restarts. Most production systems use a hybrid approach combining the best of both. Here's the recommended structure. Use Redis or similar in-memory cache for the conversational thread. This is the short-term working memory, recent messages, current task context, and intermediate results. Redis will give you fast access with built-in expirations so old sessions can clean themselves pretty automatically. For long-term memory, you should be using a vector store. This is semantic memory that persists beyond a single conversation. If a user mentions that they work at a specific company or a certain preferences, you might want to remember that for future sessions if the user wants you to remember it. Vector stores lets you retrieve the information based on semantic similarity to current context. You should be caching frequently accessed state at the application layer. If certain information gets referenced pretty frequently, keep it in the memory to avoid round trips to your database or cache. The key here is balancing complexity and capability. Stateless agents are simpler, but they are pretty limited. Fully stateful agents are powerful, but they are operationally complex. The hybrid approach gives you flexibility to choose the right level of state management for each type of information. State management isn't just a technical detail, it's a strategic choice that determines what kinds of experiences your multi agent systems can deliver. Choosing the right level of statefulness is actually dependent on your specific business use case. Now let's talk about reliability in multi-agent systems, which requires thinking through failure modes systematically because there are many more things that can go wrong compared to a single agent system. First is the failure modes you need to anticipate here. The individual agent failures are most obvious. Let's say an agent throws an error, it hits the error rate limit, or it returns a malformed response. Timeout and latency spikes can also happen when agents take too much longer than expected. Token limit can also exceed where error occurs when an agent, let's say, tries to process more context than the model actually supports. Rate limiting and throttling from API providers can also cause failures during traffic spikes. For resilience patterns, you should be retrying with exponential backoff. So when an agent fails, you should be wait and retrying again, but you should be increasing wait time exponentially to avoid overwhelming, which is already a struggling service that you might be calling. You should also be implementing circuit breakers per agent. If an agent fails repeatedly, the circuit breaker opens and stops sending requests for a cooldown period. This will prevent cascading failures and give you the problematic AI agent to recover. Here's a cutting edge pattern specific to the AI. So, reflection and self correction loops are pretty important here. Before passing output to the next agent or returning it to the user, You should have the agent critique its own work. Send the agent's output back to itself with a prompt like review this response for accuracy and completeness, and if there are any concerns, do share. If the agent identifies issues, it corrects them before proceeding. This will catch many errors that would otherwise would have propagated downstream. Having fallback to simpler logic when sophistication approaches fail is pretty important. If your multi-agent workflows fails, can you actually fall back to a single agent response that's lower quality but at least functional? You should definitely spend time exploring this. Graceful degradation strategies means that your system continues to operate at a reduced capability when things go wrong instead of completely shutting down. Maybe you can skip some refinement steps or return results with lower confidence thresholds. For monitoring requirements, you should be tracking per agent latency to identify slow agents. We should be monitoring success rate metrics for each agent as well to spot reliability issues. In addition to that, you should be also tracking cost per workflow because multi-agents can become pretty expensive, unpredictable. In addition to that, you should also implement error rate alerting for failure rate spikes. Reliability isn't optional in the production systems. These patterns need to be built in from the start, and this is not something you can design and explore after shipping them. You should be always designing for failure because in distributed systems with multiple components, failure is not a possibility, it is a certainty that you should be planning for. Now let's talk about economics and performance characteristics for multi-agent systems because these are pretty important when you're scaling multi-agent systems. For cost drivers, the number of agents invoked is a primary factor. Every agent call is an API request costing tokens. In a 5 agent workflow, you might consume 5 times the tokens of a single agent approach. Token usage per agent varies based on prompt design and task complexity. Orchestration overhead tokens are often overlooked. The supervisor in the hierarchical systems, the aggregator in parallel systems, these coordination components actually consumes token as well. Retry and error handling add cost as well when things go wrong. For latency components, sequential patterns add cumulative delay. Every agent contributes to the latency to the total. Parallel patterns are pretty limited by your slowest agent. For example, 4 agents finishing in 1 second would not matter if the 5th agent is taking 10 seconds. Network and queue overhead becomes pretty significant in distributed systems as well. Orchestration decision time is the latency added by the coordinators that they are supposed to plan or route work. For optimization strategies, semantic caching for similarity is extremely powerful and specific to AI systems. Traditional caching looks for exact query matches, which rarely happens with natural language. Semantic caching uses embeddings to find similar queries. If someone asks you, let's say for example, how do I reset my password? And you have already answered what is the password reset process, semantic caching recognizes these are the same question and they can return the cache response. This can cut the cost dramatically for your application where users are asking similar questions frequently. You should be caching common agent results when certain outputs are deterministic or slow changing. You should also consider batching similar requests together to amortize fixed cost. You should also consider setting aggressive timeouts to trigger fallback logic quickly when agents are slow. Let's say waiting 30 seconds for a response that might not come waste both time and money. Routing to cheaper models when appropriate is also recommended. For example, not every task needs your most capable model. For simple tasks, you can definitely consider using a smaller, faster, cheaper model that will cut costs significantly without impacting quality. Cost and latency optimization is an ongoing process, not a one time design decision. You should be monitoring your production metrics continuously and adjust your architecture as patterns emerge. The economics of multi agent systems can surprise you, so measure everything and optimize based on the data you're getting. Let's talk about a practical decision framework for choosing between single agent and multi agent architectures. You should be using a single agent when the task requires only one type of expertise. If you don't need specialization, the added complexity of multiple agents is not justified. Choose single agent when your latency budget is tight and you can't afford the coordination overhead. Use single agents when optimization is critical and you need to minimize token consumption. And use single agents when simplicity reduces the risk as you don't need to build complex systems from the get-go. You should start from the simplest architecture and only add complexity when you hit clear limitations. You should consider using multi-agent systems when complex workflows need decomposition. If your task has distinct stages benefiting from specialized handling, multiple agents make sense. Choose multiple multi-agent systems when parallel processing can reduce latency. If you have independent subtasks that can run concurrently, the speedup might justify the extra cost and complexity. You should consider using multiple agents when you need different specialized capabilities. If your workflow requires legal expertise, let's say financial analysis and technical evaluation, separate agents can perform different duties and will produce generally the better results than one generalist agent. Consider multi-agent when you fault isolation can also improve reliability here. If failures happen in one part shouldn't bring down the entire system, then multi-agent systems are recommended. For your production checklist, you should define clear agent boundaries. Each agent should have a well-defined responsibility. You should definitely implement human in the loop checkpoints for high stakes decisions. Before executing important actions, you can have a human review and approve the agent's proposed action. This is standard practice in production AI systems. You should consider implementing comprehensive monitoring from day one as well. You can't debug what you can't see, so you should plan for partial failures explicitly in your design and have monitoring set up. For example, how does the system behave when agent B fails but agent A and agent C succeed? You should model your cost before deployment as well. Multi agent systems can surprise you with token consumption, so run realistic scenarios and calculate the project projected cost before committing to the design.